Next, we're going to tackle hydrogen bonds. And while these are weak bonds, they can be a little bit hard to comprehend. So we'll spend some time on this. By definition, as is stated on this slide, it says that a hydrogen bond forms when a hydrogen atom covalently bonded to one electronegative atom is also attracted to another electronegative atom. That's a mouthful and honestly probably doesn't make a lot of sense. So let's tease this out. So let's draw a water molecule. You've got oxygen and two hydrogens, right? That oxygen is held to those two hydrogens using single covalent bonds. But remember, these covalent bonds are polar, right? The oxygen is very electronegative. It hoards electrons towards itself, so it develops a partial negative charge. The hydrogens don't have much control over the electrons, so they lose some of that negative charge, and so they're going to be a little bit more positive. Now, when you have a lot of water molecules bouncing around together in your water bottle, right, you're going to have these water molecules bumping into each other. And when they bump into each other, we talked about how opposite charges are going to attract. You have a negative oxygen here. You got a partial negative oxygen here. Again, the hydrogen's partially positive. That was terrible. Partially positive, that one's better. So when you have water molecule 1, 2, and 3 all bouncing around and bumping into each other, you're going to have an attraction between this positive and this negative charge. This positively charged hydrogen is positively charged because it's bonded to this really electronegative oxygen that hoards the electrons towards itself. It's going to be attracted, to this negatively charged oxygen of a different water molecule. And that involving the hydrogen is a hydrogen bond. Another hydrogen bond will form here, right, between this hydrogen and this oxygen. All right, so again, a hydrogen bond forms when a hydrogen atom, like this one in the water here, is covalently bonded to an electronegative oxygen. It will develop that partial positive charge, and it will be attracted to anything else that has a negative charge. On this slide, we have, instead of another water molecule, we have the water molecule on the top being attracted to a molecule of ammonia. Nitrogen is also quite electronegative, hoards electrons towards itself, develops that partial negative charge, and so that nitrogen with its partial negative will be attracted to any other hydrogens in that same solution that have that partial positive charge. I'll give you a hint. An easy way to identify the 3 different kinds of chemical bonds that we've talked about so far in a drawing in your textbook or on the slides. Covalent bonds are drawn as a solid line. So in the molecule of water or in the molecule of ammonia, the nitrogen and the hydrogen, or the oxygen and hydrogen, are bonded to each other using those covalent bonds, solid line. If you see a dotted line between a hydrogen on one molecule and another fairly electronegative atom on another molecule, that dotted line is going to represent a hydrogen bond. So solid line covalent, dotted line with a hydrogen is a hydrogen bond. And then ionic bonds will never show a line, solid or dotted. You'll just see 2 atoms or molecules that have opposite charges really close together, and full opposite charges. All right, last type of bond that we're going to talk about are these, what we call van der Waals interactions. These are also kind of tough to comprehend. But if you think about matter, right, anything around us, the computer, a pencil, a piece of paper, all of these pieces of matter are made out of atoms. You have protons and neutrons and electrons in there. And these electrons, you can't see them, but they're constantly buzzing around their atomic nuclei. And it's just by random chance that you might have suddenly, and for a very brief time, a whole bunch of electrons accumulating in one spot in this body of matter. And then other places where there's a void of electrons, just because they're buzzing around so quickly and randomly, right? And so these fleeting pockets of charge can actually attract to each other when you have two bodies of matter with these fleeting pockets of opposite charges close enough together. And the attraction between these fleeting pockets of opposite charge are what we call van der Waals interactions. And some organisms exploit these van der Waals interactions, like the gecko. Geckos can walk up walls and ceilings, and they do this because they're using those pockets of opposite charges that stick to each other to help them walk up the wall, right? So the fleeting pockets of charge on the foot pads and the fleeting pockets of charge on the wall attract to each other, and that's enough to carry the gecko up the wall or up the ceiling. So individually, the fleeting pockets of charge, when they're attracted to each other, really don't have a lot of force, but collectively, if you have enough of them, it can be really strong. And engineers have actually exploited this. They've looked at the way that the gecko's toe pads are organized, and they've made synthetic material that they call gec skin. Read about it in your textbook, but a small no-card size piece of this gec skin just placed up against the wall, no nails, no glue, nothing, can hold several hundred pounds stuck to the wall. So it's pretty impressive. I'm not gonna lie to you. Okay, so one of the last things that we're gonna cover in chapter 2 is now looking at molecular shape, and we're going to come back to this point in chapter 4 as well when we start building biologically relevant molecules. But I already stressed earlier in the chapter that a molecule's shape is really very important to its function. If it doesn't have the right shape, it's not going to be able to accomplish its job. And so you might be asking, well, what determines the shape of a molecule? And this is really determined by the types of atoms that are used to build the molecule and the positions of the atom's orbitals. Remember, an orbital, all I want you to know is that it's that three-dimensional shape where an electron spends the majority of its time. And so if we go back and we look at an example of an atom here with its different orbitals, you see the spherical orbitals and the dumbbell-shaped orbitals. When they all kind of come together superimposed over the atomic nucleus, they kind of hybridize, they merge together, and they create kind of a tetrahedral shape to that particular atom. And then as you build molecules with multiple atoms with these tetrahedral shapes, that gives then a resulting full shape to the actual molecule. And so maybe you've noticed that water molecules are never drawn as a straight line, right? It's never H, O, and H. It's always got a bend in it. And this bend is because we've got to create space for these electrons and their orbitals to fit together when you're bonding together the oxygen with the hydrogens. And so water fits pretty well in this tetrahedral theme, right? You've got the oxygen in the center, and you've got the two hydrogens in the water molecule in two of the vertices of the tetrahedron, and then unbonded electron pairs in the top and the bottom. A molecule that fits even better into that tetrahedral theme is methane. So methane has a single carbon in the middle. And then remember, carbon has a valence of 4, right? It can form 4 bonds. It needs 4 more valence electrons, and so it can get those 4 more by utilizing covalent bonds with 4 different hydrogens. And so this molecule fits perfectly into that tetrahedral shape. The carbon goes on the center, and then each of the hydrogens will fit into one of the vertices of the tetrahedron. Now, these molecules are pretty simple. Let's take a look at something more complex, and just to show you, giving you an idea of where form and function of a molecule are really important. So this molecule in the center is really complex. This is an endorphin. This is a molecule that your body naturally produces under certain conditions. Endorphins are produced after exercise. If you've heard of runner's high, right? It makes you feel good when this endorphin is released after you exercise, or after sex, endorphins are released. And also when an individual experiences pain. So endorphins can not only make you feel good, but they also are your body's natural painkiller. And the way that they function is these endorphins are produced by your body, and they have the ability to bind to receptors on the surface of your brain cells, telling the brain cells, don't feel as much pain, everything will be fine, no need to freak out. Now, that's a natural painkiller. If you've ever been injured or gone through surgery, you may have been prescribed morphine. And you know that morphine is a really strong painkiller. And the reason why morphine as a molecule is a really good painkiller, and our bodies can respond to it, is that it has a similar structure, molecular structure, to our natural endorphin. So it's kind of strange, right? Morphine is not something your body produces, and yet it has the ability to react to it, which is kind of crazy. There's an explanation for this. If you looked at the boxed region of the morphine molecule and the natural endorphin, you'll notice that that boxed region, the shape of the molecules are very similar. And in fact, this is the actual part of the molecule that interacts with the endorphin receptor on the surface of your brain cells. So your brain cells don't know any better. If something binds to the endorphin receptors, it says, okay, I'm not going to feel pain, I'm going to be happy. It doesn't matter whether it's morphine, a molecule that comes outside your body, or the natural endorphin that your body itself produced. If morphine didn't have that shape in that position of the molecule, we wouldn't use it as a painkiller because it wouldn't be able to accomplish that particular job.